To the week 3 NPTEL previous year assignment solving section. Myself Suraj P from Chemical Engineering Department, IIT Kharagpur. So let's start the session. First we can see it's meant by McCabe-Thiele method. McCabe-Thiele is a graphical method used for determination of number of equilibrium stages required for separation of two components. So the main assumption in determining the number of stages by graphical method is there is equimolar flow of liquid and vapor phase throughout the column. So if Vn is the flow rate of vapor from stage n, then Vn will be equal to Vn plus 1, where n plus 1 is the vapor flow rate in stage n plus 1. And this is in moles per time. Similarly, Ln is equal to Ln minus 1. So, and where Ln is the flow rate of liquid from stage n and Ln minus 1 is the flow rate of liquid from stage n minus 1. So the constant molar overflow assumption is true only when molar latent heat of vaporization of each components are same and there is no heat of mixing between the components and the heat capacities are constant and there is no external addition or removal of heat. And these assumptions are valid for chemically similar compounds like adjacent numbers of homologous series, isomers, isotopes, etc. So see the mass balance on a distillation column. So here we can see the figure of a distillation column where feed is entering at represented by F and the mole fraction of the feed is represented by XIF. D represents the distillate flow rate, XID represents the mole fraction of distillate, more volatile component in distillate. B represents the bottom flow rate and XIB represent mole fraction of more volatile component in bottom product. So bottom, then the overall mass balance is given by F equal to B plus D and the component mass balance is given as F into XIF equal to D into XID plus B into XIB. So let's see the operating line equation for rectify section. So we have previously told there are two sections in distillation column. The top section above the feed plate is known as rectifying or enriching section and the bottom section below the feed point is known as stripping section. So the operating line equation for rectifying section is, first we need to do the component and total balance for the rectifying section. So if V represent the vapor flow rate from the overhead of distillation column and L represent the amount of liquid that is recycled back to the column and D represent the distillate that is collected as top product, then from the balance we can see that V equal to L plus D. Also the reflex ratio R is given by the ratio of liquid that is drawn back to column and distillate that is collected as product. So R is given as L by D. And on substituting this R in equation V equal to L plus D, we will obtain V equal to R plus 1 into D. So performing component I balance in the rectifying section, we will get V into Yi n plus 1 equal to L into Xi n Ni plus D into Xid. So after dividing this equation throughout by vapor flow rate, that is V, we will obtain this equation and followed by substitution of the total mass balance, we will obtain equation of operating line for rectifying section. From here we can see that this is in format of Y equal to mx plus c, where m is the slope and here the slope is r by r plus 1 and the intercept is xd by r plus 1. So a line with slope r by r plus 1 and xd by r plus 1 is drawn from point xd to obtain the operating line of rectifying section. So next we can see operating line for stripping section. So stripping section is the section that is below the feed plate. Let L dash and V dash represent the liquid flow rate downward and vapor flow rate that is upward. So performing a total mass balance in this section, we will obtain L dash equal to V dash plus B, and a component balance L dash into XIM equal to V dash into YI M plus 1 plus B into XIB. After this, we will divide it throughout by V dash and move this B XIB to left hand side. We will obtain the equation of operating line in stripping section for the stage M plus 1, which is given by YIM plus 1 equal to L dash by V dash XIM minus B by V dash XIB. So the slope of this stripping section operating line is L dash by V dash. So if we draw a line from point XB to the equilibrium line with a slope L dash by V dash, we will obtain the stripping section operating line. So next one is a problem which is based on McCabe-Thiele plot. So here they told that 120 kilomole per hour of feed containing 30 mole percentage hexane and 70 mole percentage heptane is to be distilled in a distillation column. The bottom product contains 20 mole percentage hexane. Liquid product from overhead total condenser is accumulated in an accumulator. The overhead product rate from accumulator is 70 kilomole per hour. If 60% of the product from the accumulator is reflexed back to the column, then what is the intercept of rectifying section operating line in the McCabe-Thiele plot? So here the feed flow rate is given 120, and the mole fraction of the more volatile component, that is hexane, is given, which is represented by XF, and the bottom product contains 20 mole percentage hexane, so this is XB. Also the distillate flow rate is given by D. So and we are asked to find the intercept of rectifying section operating line. So we know the equation of rectifying section operating line, y equal to r by r plus 1 x plus xd by r plus 1. This xd by r plus 1 is the intercept. So first we can draw the figure of distillation column. So this is F is equal to 120. This is the condenser. After condenser, accumulator is from their accumulator. We will draw the distillate, and some part is moved back to column as reflux. So this is the reboiler. Bottom product, top product flow rate is given as 70. So from total balance we will obtain the flow rate of bottom as 50. XF is equal to 0.3, XB is equal to 0.2. Also, it's given that 60% of the product from accumulator is reflux back. So from here we can find out the reflux ratio. 60% is product is reflux back, so remaining 40% will be drawn as distillate. So the reflux ratio will be given by L by D. L is the quantity refluxed back, that is 60, and quantity that is drawn as product, that is 40. So R is coming to be 1.5. So here we need to obtain XD also to find the intercept. R we have already obtained as 1.5. So for obtaining FD we need to do component balance, hexane balance. So F into XF equal to D into XD plus B into XB. So on substituting 120 into 0.3, let's see, 120 into 0.3 equal to 70 into XD plus 50 into 0.2. So from here we will obtain XD is equal to 0.3714. So on substituting this XD in this equation, where XD by R plus 1 is obtained as 0.15. So, the answer for this question will be option A. Let's move to next question. Chimney tray in a fractionator is used to dash. It is dash as a fractionating tray. So we know that chimney tray in a fractionator is used for withdrawal of side stream, and it is ineffective when compared to other trays. So it is not considered as a fractionating tray. So chimney tray is used for drawing of liquid from any tray in a fractionating column. So this is the fractionating column where chimney tray is located here. So it has some riser in it through which the vapor rises. Here the vapor rising through the riser does not come in contact with the liquid, so no interface mass transfer occurs between the vapor and liquid, so it cannot be considered as a fractionating tray. This is the riser. Next one, question number 3. In a fractionating column bottom pressure is always dash than column top pressure. We know that the column bottom pressure is always higher than the top pressure in order to allow the vapor to flow from bottom to top. Answer for this question will be C. Column bottom pressure is higher than column top pressure to enable vapor flow from bottom to top, and the equation for finding column bottom pressure is sum of column top pressure and pressure drop across each tray times number of trays. A typical pressure drop across each tray is 50 mm water column. Next we can see the thermal condition of a feed. Thermal condition is the number of moles of saturated liquid produced on the feed tray per mole of feed. It can be determined by this equation where HV minus HF is the heat required for vaporization of 1 mole of feed, and HV minus HL is the heat of vaporization of 1 mole of liquid feed. Q is the feed quality, or it can also be told as thermal condition of the feed. Based on the Q values, we can decide the phase of the feed. If Q is equal to 1, the phase of the feed is saturated liquid. If Q equal to 0, phase of the liquid is saturated vapor. When Q greater than 1, the phase of the liquid is subcooled liquid. And if Q is less than 0, it's a superheated vapor. And if Q is fractional, the feed will be entering as a mixture of liquid and vapor. Slope of the Q line, which is also called as feed line, is given by Q by Q minus 1. Q by Q minus 1 is the slope of the feed line. After substituting this Q value here, we will obtain for Q equal to 1, the slope will be infinite. Similarly, we can find the slope for other cases. Here we can see how the Q line varies depending on the feed quality, phase of the feed. So if Q equal to 0, the Q line will be a horizontal line. If Q equal to 1, it will be a vertical line. It should also be noted that Q line passes through the intersection of operating line of enrichment and stripping section. Here the enrichment operating line and stripping operating line is also to be seen, and the Q line will always pass through the operating line of enrichment and stripping section. If you draw the stripping section operating line, suppose if the feed quality is saturated liquid, and if you draw the operating line for stripping section followed by operating line of enrichment section, both of the line meet at this point, and it always pass through the point of intersection of enrichment and stripping operating line. This is the operating line for stripping section. And this is the operating line for enrichment section. Next question, question number 4. Match column 1 containing feed condition in distillation column with column 2 containing Q factor. Here some feed quality is given and the corresponding Q value is given. So we are asked to match feed condition with respect to Q value. Here from previous slide, we can see that if liquid is entering at its bubble point, what is the Q value? Liquid is entering at the bubble point, Q value is equal to 1. And if liquid is vapor feed at its dew point, then its Q value is equal to 0. If liquid is partially vaporized feed, then the Q value will be between 0 and 1. And if feed is superheated vapor, then Q is less than 0. The correct option will be 1D, 2B. Correct option will be B. Moving to next question. Composition of distillate in a fractionator depends on column pressure, column top temperature, both A and B, none of these. The composition of distillate depends on both column pressure and column top temperature. The answer for this one is B. So the distillate vapor leaving the top tray is at its dew point at the column top temperature and pressure. If we change either temperature or pressure, the distillate composition will also change accordingly. Next, let's see what is meant by total condenser and partial condenser. In a total condenser, all the vapor leaving the top stage is condensed to produce a liquid top product called as distillate. Here, all the product that is coming from the overhead of the tower is condensed and moved to accumulator. Only a part that is required for reflux is only recycled black, and most of the product is drawn in liquid stage. But in partial condenser, only the overhead product is only partially condensed condensed to the accumulator and drawn as vapor. If we desire vapor as top product, then we will use partial condenser. And it should be noted that in a McCabe-Thiele plot, the partial condenser will be considered as a theoretical stage, as here the both vapor and liquid contact are there and both are at equilibrium. So a partial condenser is considered as a theoretical stage. Also the reboiler is also considered as a theoretical stage. So if we obtain from McCabe-Thiele plot say 10 stages, so only 8 trays are required. Remaining one will be reboiler and one will be partial condenser. But in case of total condenser is used, 9 trays will be required and one reboiler will be required. Moving to next question, choose the correct statement about multi-component distillation. The lightest component in distillate is known as light key. No, it is not a correct statement. The lightest component in bottom product is the light key. The heaviest component in bottom product is known as heavy key. This is also an incorrect statement. Actually, the heaviest component in the distillate is known as top product is known as heavy key. And the volatility of split key is between volatility of light key and heavy key. This is a true statement. And split key is present only in bottom product. This is also a false statement. So the correct answer will be option C. Moving to detailed solution, multi-component distillation. We have several terms like light key, heavy key, and split key. Light key is the lightest component in the bottom product. Similarly, heavy key is the heaviest component in the top product. Component lighter than light key will be going to overhead product, and components heavier than heavy key will be going to bottom product. And the split key refers to the component with boiling point between light key and heavy key. The split key will be distributed between top and bottom product. Moving to question number 7. Choose the incorrect statement among the following. In case of liquid or partially vaporized feed, spacing above the feed tray is kept higher than normal tray spacing. This statement is true actually, and spacing below the bottommost tray in the fractionating column is higher than normal tray spacing. This is also true. Then both rectifying and stripping section operating line coincide with x equal to y line under total reflex condition. Under total reflex condition, R will be equal to infinite. The operating line for rectifying and stripping section will be coinciding with x equal to y line. Also, there will not be any bottom product drawn at during total reflex. So this statement is option C statement is also true. As the reflex ratio in a distillation column is increased from minimum, the total cost first increases and then decreases. The option D is an incorrect statement. On increasing the reflex ratio in a distillation column, the total cost first decreased and it will increase again gradually. So let's see what is meant by optimum reflex ratio. We have two terms, R minimum and R infinite. R minimum is the minimum reflex ratio where we require infinite number of theoretical stages. R infinity is infinite reflex ratio where we require minimum number of theoretical stages. And there is a term called R optimum, which is optimum reflex ratio for most economical operating condition. And this R optimum will always lie between R minimum and R infinite. When the process will be economical, most economical, the total cost will be minimum. That is, sum of operating and capital cost will be minimum. Here R optimum lies between R minimum and R infinity. So the next one is the total reflex condition. At total reflex D equal to 0 and R tends to infinite. So the operating line equation for rectifying section will be R by R plus 1 will be equal to 1 and R tends to infinite. So this line will be equal to 1 and xd by R plus 1 will be equal to 0. At total reflex y equal to x, and for stripping section b equal to at total reflex b equal to 0, as no bottom product is drawn, as we can see from here, b equal to 0 and t equal to 0. And here also the stripping section line equation will be equal to y equal to x. Both rectifying section line and stripping section operating line will coincide with equilibrium line, not equilibrium line, and y equal to x line. This is the y equal to x line, and it should be at 45 degree with respect to yx line. Right. Total reflex operating line for both rectifier and stripper line lie on 45 degree diagonal. The point of intersection is not dependent on the feed combustion and Q line. Total reflex gives minimum number of equilibrium stages for separation, that we have already told. From here also we can see that total reflex gives minimum number of equilibrium stages. If there are some distillate and bottom product drawn, then the equilibrium stage will be higher. So let's discuss about the total cost increase or decrease with increase in reflux ratio. The total cost has two components. One is fixed cost, where the distillation column cost, internal cost, reboilers and condenser cost include. Another is the operating cost, which is associated with operation of distillation column. So for operation of column we need condenser, reboiler, cooling water, steam and pumps. This condenser is required for cooling the top product, reboiler is and steam is required to reboiler and steam is required to heat the bottom product, and the pump is required in both for reflexing the top product and also for reflexing the bottom. Also it is required for feeding the column. At R minimum, fixed cost tends to infinity. Here we can see at R minimum the fixed cost is tending to infinity, as infinite number of trays are required in minimum reflex condition, and operating cost will be minimum as minimum utilities are required. On increasing the R, lower number of trays are required and fixed cost initially decrease, but the column diameter required will be increasing, so that fixed cost eventually increase. This is the fixed cost or total cost. It's also called as annualized cost. And this is the operating cost. Hello.
Option C.
Option C. Yes, option C is the correct answer. Then let's see what is the detailed solution. So for multi-component distillation, it's difficult to use McCabe-Thiele method. So we will use some analytical expression for estimation of number of stages and minimum flux ratio. So there are four analytical methods. This Fenske equation is used for estimation of minimum number of ideal stages. Underwood equation is used for minimum reflux ratio determination, and Gilliland equation is used for determination of theoretical number of stages, and Kirkbride equation is used for feed plate location. So first we can see the Fenske equation. From Fenske equation we will get an approximate value of minimum number of equilibrium stages, which is at total reflex condition. So this is the equation for finding minimum number of trays, and XLK is the mole fraction of light key, XHK is the mole fraction of heavy key. Similarly, alpha LK is the average value of relative volatility of light key and heavy key. So the average value is determined by geometric mean of relative volatility of light key by heavy key in the distillate in times relative volatility of light key to heavy key at the bottom. Next is Underwood equation. Underwood equation is used for estimation of minimum reflex ratio. This is the equation where one theta value is given. First we need to fix the feed quality, then we will be able to find theta value. Then this theta value can be identified by trial and error method. After obtaining theta, we can substitute that theta in this equation. From there we can find the R minimum value. Next is Gilliland equation. Once minimum number of stages and reflex ratio are known, number of equilibrium stages can be determined from actual reflex ratio. So this is the equation. Previously we have obtained n minimum and r minimum. If we fix one operating reflex ratio, that is r, we can find the number of equilibrium stages for that case. So this can be found out from equation or from plot also we can find the n value. Next is Kirkbride equation. Kirkbride equation is used to locate feed tray from the ratio of number of equilibrium stage above and below the feed point. So m is the number of equilibrium stage above feed point and p is equilibrium stage below feed point. So this ratio can be found out. Next one, consider that in a batch distillation operation for separation of binary mixture, the first drop of distillate is produced at time t1 and then distillation continues till time t4. The distillate liquid is collected in an accumulator vessel that can be considered to be well mixed. The composition of distillate in the accumulator vessel at different instants of time is measured and tabulated in table below. So we are asked to find the relation between T1 and X average. So this T represents the time of collection of distillate and the respective composition of distillate collected is represented by XD average. So, uh, so can someone answer this question?
Option A.
Option A.
Option A.
Actually, this XD average is the more volatile component. Uh, so with increase in time, the value of more volatile component will decrease. So
Option B.
option B, yes. So the answer for this is option B. So for batch distillation is an unsteady state operation, and the average composition of most volatile components in the distillate decrease with progress of time. So with increase in time, the composition of the distillate will decrease. Next question. Cut specification in a batch distillation process may be controlled by. How can we control the specification of uh, product in batch distillation? Can someone answer this?
All of the above.
Yes. All of the above is the answer for this. Thank you for listening. If you have any questions, can you please ask?
Sir, in a partial condenser,
Uh,
how partial condenser act as a plate stage?
Here actually there is a contact of both vapor and liquid, so it's considered as an equilibrium stage in partial condenser. Both vapor will also be there, some liquid will also be there. Uh,
Thank you, sir.
We can the question come up. If we were having a program as well.
Professor Ray, you are not audible.
Can you hear me now?
Yeah, yes.
Then I have some problem.
Suraj, please mute yourself. Suraj, mute yourself.
Am I audible now?
Yeah, it's fine now.
Okay, let's see. In fact, I'll start answering earlier question. That is, I will condenser and consider it to be a stage of fractionation. That Suraj has learned that only one of the overhead material is cooled, condensed, and it's in the accumulator. The non-condensed goes off on the face of the so quite naturally the vapor there is expected to be the liquid on vapor which leaves the vapor space of the platform leave gain. In fact, was it that vapor is there in the vapor space? Yes, that's true. Yeah, today there will be a small it that's from that
Professor Ray, I'll just interrupt you once. Students, can you hear Professor Ray clearly?
No, ma'am. Voice is not clear.
Yeah, the voice is not audible. That is what I was also thinking. So today there is some
that's true because I have lost my connect.
If you can just rejoin once more, it will be better. Somehow the connection is very unstable today.
Do that.
I think if Professor Ray leaves and joins once more, it's going to be easier. Am I audible to all of you?
Yes, ma'am.
Yes, ma'am.
Okay. So just to clarify, I'll mention that see you require partial condensers when you desire or when the requirement is for a vapor product, right? Under that condition, anyhow, you will be requiring some amount of liquid because the reflux is going to be a liquid. So therefore, you need a vapor as a product. It can also happen that you can need a vapor liquid mixture as a product, but you need liquid as a reflux to the column. So quite naturally under that condition, what happens is that there has to be some sort of a liquid vapor mixture in the condenser. The condenser does not condense the entire vapor which enters the condenser from the top tray. It partially condenses the vapor and the condensed liquid, either totally or a part of it, is sent back as the reflux. As a result, under this particular condition, the condenser also behaves as a single ideal stage. So therefore, typically what you do, when you calculate the number of stages from the McCabe-Thiele method, suppose you get 10 stages from the McCabe-Thiele construction, then we say that the actual number of ideal stages inside the column is 9, because one stage, the reboiler acts as a vapor liquid separator, and therefore one stage accounts for the reboiler. When you have a partial condenser, then if you have found out that the number of stages from McCabe-Thiele is 10, then in that case, the number of stages inside the column is going to be 8. One of the stages is going to account for the reboiler and the other is going to account for the partial condenser. Am I clear to all of you?
Yes, ma'am.
Yes, ma'am.
Professor Ray has joined, so possibly he'll like to add up something regarding the partial condenser.
No, that's right. That's absolutely complete. So we can, if they have any more question, we can to discuss. We still have some time to test.
Somehow your voice is broken. It's getting broken. So if you switch off your video, it will be better possibly. Professor Ray,
My video, okay.
the video, if you switch
The
off, it
video
will be
switched
better
off. Okay,
possibly.
now.
Any other questions, please?
I think my
Any other questions, please?
Yes, ma'am. Yeah, ma'am. Yeah. At what basis wear height and downcomer width is decided in general if we talks, ma'am?
The downcomer height and the downcomer width. Am I
No,
clear?
ma'am. No, ma'am. Wear height
Yes,
and yes, ma'am. On downcomer width.
I see. Wear height and downcomer width. Professor Ray, will you clarify or should I continue?
I think I'll prefer to respond to that.
Yes,
See,
please.
it's like this. On trays, you have vapor disperser units. What are these? These are the valves, these are the bubble caps, or it could be the seals, in fact. In order that there is a vapor liquid contact on the tray, these have to remain submerged. The amount of submergence will depend on the level of liquid on the tray, and the level of this liquid has to overflow over the wear and go to the downcomer and fall to the next tray. So quite naturally, the level on the tray is decided by the height of the wear over which the overflow occurs. So the depth of liquid required on the tray decides the height of the height of the wear that you are supposed to provide. Now comes the question of the downcomer width. It's like this. The liquid falls from the downcomer above to the tray, flows over the tray, goes to the downcomer by crossing over the wear, the outlet wear, and falls to the next tray. It is possible for you to have a larger downcomer width. Yes, true. But if you do that, the space over which you shall be allocated, which you will be providing your vapor dispersers, will become less. On the other hand, if you have too less amount of space for your downcomer through which the liquid has to travel by gravity to the next tray, the downcomer liquid backup may be so high that it may get flooded. So there is a balance. In fact, there are ways to calculate the backup in the downcomer, and the downcomer typically width is a standard value. I think, I don't remember exactly, possibly we can, Professor Das may correct me, it's around 76% of the diameter, typically.
Yes, that's true. 76%.
Yeah. I mean, 76 is not sacrosanct, it could be 76, 78, 74, but it's of this order. Very common is a 76% figure. I mean, does it satisfy your question? I mean, your what you're looking for?
Yes, sir. Downcomer width is understand, but wear height. If I am talking about the what, how much in should be the height is optimum height, sir.
Okay, right. Okay. If you want a higher submergence, you have to go for a higher height of your wear. Now, suppose you are using 4-inch bubble caps. The 4-inch bubble caps will have typically around, say, 65, 70 millimeter of height. all the slots have to be submerged. Not only the slots have to be submerged, above the slots also, above the cap head also, there should be a level of liquid. So naturally, your tree of certain height, which will ensure this. If it is a sieve tray, possibly you may not require this height, maybe 5 millimeters. In fact, these are also standard figures. These are also standard figures. If you refer to, in fact, you can refer to our book also. And what we can do is we can give you these standards if you're interested. Maybe we can ask Mr. Suraj to post it if you require.
Okay, sir. Thank you.
Thank you. Anything else? In fact, really, if you really want to calculate the downcomer backup and width and such things, refer to the book by, you can refer to our book also, and there are quite a few other books which will give you this book on column hardware design.
Sir, can you post it the book name in message box either?
Sure, not right now, but definitely it will be done.
Okay, sir.
I'll ask Mr. Suraj to do it. In fact, most of these are during design, you have certain specific design options, you choose from those. The something consideration is your height of your test should be sufficient so that all your vapor dispersers remain well submerged. Anything else? We still have a little time. In fact, whatever distillation column related things that we had are related to conventional columns only. There are other specific cases where more complicated column situations are handled. Those are not covered here as such. One such example is basically your pressure control in your stabilizer top, with a bypass valve and all. So those things are not covered here.
Well, I've posted the book title in the message. So if you wish, you can see it. It can also be posted by Mr. Suraj in the question forum. Any other questions, please?
Sir, we have 10 minutes. Can you talk about the pressure controlling and how many types of pressure controlling available in the market, sir, as of now, sir?
If you're talking about pressure control, are you specifically talking about column top pressure control?
Yes, sir, column top pressure control by hot vapor bypass and condenser backup like that, sir.
Okay, I'll put it like this. See, it's
But this is also discussed in quite detail in this book. That is true. So just before Professor Ray proceeds, I just have one particular, I wish for one particular feedback from one of you. Can you just give some feedback regarding the course or the assignments in particular? Because if we can have your feedbacks, then accordingly we can modify the course and the assignments, etc. So any feedback from your side?
Ma'am, course and assignments is very useful for design, and I am also like to include some renewable energy related design if it is possible for anaerobic digestion digester design.
I see. That let's see if we can do something, but if you can post your doubts, we can definitely address them. And have you registered for the exam, or you will be doing it later, or what is it? What are your plans?
I am planning for registering exam also.
See, till now we have not included anything, but if you can post some of your doubts, etc., then I or Professor Ray, we can take it up during the interaction sessions or during the question forum sessions which we'll be having. Well, now I would any other comments or doubts. Otherwise, I'll request Professor Ray to carry on with the pressure control systems.
Thank you, ma'am.
Yeah. Anything else? Any of you? And Professor Ray, you may continue.
Yeah. See, the next 8 minutes, what we have, I'd like to be very brief and would like to just illustrate the principles. See, in any distillation column, whatever you distill, there will be some amount of non-condensables which will be coming in, which will not be condensing in the overhead condenser. It could be the air which was dissolved in the feed, or it could be a small quantity of very light hydrocarbon or any other light component which does not condense at the condenser temperature. The condenser definitely will be using the standard coolant, possibly cooling water, or it could be any other coolant also. So it happens that it does not condense. The pressure control of this column primarily is done by controlling the bleed of this non-condenser gases. So the main pressure control is by controlling the outflow of these gases. If you throttle the outflow of the gases from the overhead vapor space of the reflux drum, the pressure increases in the reflux drum, the pressure is in the condenser from where the material comes to the reflux drum, and the column top pressure also increases. So ultimately, in order to control the column top pressure, the convention is to throttle non-condensable venting, or rather non-condensable disposal line, which takes out the non-condensables from the vapor space of your reflux drum. This is the movement. But I understand that some of you have a refinery background and possibly interested in knowing the other ways of considering, or rather other ways of controlling the overhead column pressure. And one such example is there in most of the refinery stabilizers, where the top product is primarily LPG. There may be some small quantity of non-condensable gases which are being used. It depends the amount that happens here.
Professor Ray, I'll just interrupt you. Can you? Is Professor Ray audible to all of you?
No, ma'am, voice not clear, ma'am.
Yeah, that is the problem, because repeatedly I find
Oh,
that his voice is getting means broken or something, and we are unable to hear you properly.
has it improved now?
There's one thing,
Not
Professor
possible.
If, which I can suggest. See, it's time after the assignment 4, after the 4th week, we have to go for the first interaction session. So it will be very good. I'll request all of you to post your doubts, etc. So that in the interaction session, definitely it will be done from the studio. So therefore, the audio, video, everything will be much better. So if you can just post all your doubts, we are going to collect all these, and we are going to discuss these in the interaction
Excellent.
session, which we will be having maybe in say 2 weeks time or something. That
Okay,
discussion.
okay, ma'am. Thank you. I will post you mail or other kind of form. So,
Yeah, in the question forum you posted, then the TAs, Mr. Suraj and Mr. Amir, they'll collect the questions. So therefore, maybe in next week or sometimes we are going to have the first interaction session. At that time, Professor Ray or myself, we can discuss all the doubts that you have. So I'll request you to post those questions there, so that we can take up the questions and discuss them in the interaction session. Today, somehow or other, the connection.
That would be nice.
thank you. Thank you, sir.
Today, somehow or other, the connection is very unstable. I do not know why. So, could you hear what I was telling for the past 4-5 minutes?
Yes, ma'am.
Okay. So, I request you again, please post your doubts, and Mr. Suraj and Mr. Amir will be collecting them, and we'll be discussing those in the first interaction session. Maybe within a week or two, we are going to have it.
That would be nice.
So, if we have
So
no
we'll
other
stop it
discussion,
now.
yes, please, Professor Ray.
No. Yeah, that, let's end session now.
No, at least I cannot hear you properly.
Okay.
Possibly the connection is very unstable. So we'll discuss with Suraj next week. We hope that you have a much better connection. And we'll be discussing again with you. So if there are any other doubts, discussions, you can collate all your doubts and we'll be taking them up either the next week. I hope by that time we have a much better audio and video system, or in the interaction sessions, we are going to discuss all these issues with you.